For this problem, we're going to be trying to find the minimum thickness that we can have in our cylinder, or in a cylinder filled with some type of gas, in order for that cylinder to not deform at all or fail. So we're going to have some cylinder like this. With some sort of thickness. So I'm just going to make that our thickness a little t. So the way we want to look at this problem is we have this gas inside of our cylinder that's exerting some type of pressure on each of the sides of the cylinder, which is trying to pry it apart. So we have some forces coming like this. These pressure forces are all coming right at the inside of that cylinder, trying to pry it apart. And we're trying to find this thickness that we can, that minimum thickness that we can have in our cylinder in order for no deformation to happen. So what I'm gonna do is take the top circle of our cylinder and I'm gonna give it an axis system, Y and X direction. So we have each force coming in on that circle at some theta. And where we want to look at this is we want to take each area at where that pressure force is being exerted. So we're going to have each area on the cylinder like this. So we're going to need that height of that cylinder in order to find each of these little cuts that we have made. So where those cuts are, we're going to have an arc length like that. So I'm going to actually make our theta, I'm going to turn that into a d theta, since that's going to be changing as we, wherever we're at on our circle. So then we're going to have some radius of that circle I'm going to label as r. And this arc length is then going to be our r times the d theta. So right here we have essentially what our area is. We're going to multiply that by our h eventually to get that total area. So now we obviously have some type of material that our cylinder is made out of, and that cylinder is going to have a tensile strength, which will matter for how much force that cylinder can take, depending on what material we have. So we have some tensile strength. We're going to multiply that by 2 for our cylinder, and then we're going to have our thickness times our height. So this is what our total force is going to be that we're going to use to set equal to each of these pressure forces that we find, the total of our pressure forces for each of these areas. So that will eventually give us what our thickness is. But first, we're going to want to figure out our total forces for these pressures that we have. So I'm going to do Fx equals each differential force. So one thing to note is we're taking in the x direction, so we're going to want to add cosine of theta to make sure that we're only getting those x forces. So now what I'm going to do is, as you can see, we're going to have this differential force is going to be our pressure times our differential area, then times the cosine of theta. Now when we look at it, we can see that our differential area is actually going to be, we can look at it as each of these cuts. So our differential area will just be our radius times our d theta times our height. So I'm going to write that out again. So it's going to be our pressure times our radius times d theta times our height. So we can already see that some of these terms times cosine of theta. So we can already see some of these terms can be pulled out of the integral. So I'm just going to pull those out, which is going to be our p, pressure, our radius, and our height can all be taken out because those are all going to be constants. So now all we have is our cosine theta, d theta, and now we need our limits. So we're going to take all these pressures from just half of the circle. So our limits are just going to be negative pi over 2 on the bottom and pi over 2 on the top, since we're just doing half of that circle. So I'm going to put that, label that on here. So now we're just going to integrate this. So it's just cosine theta, and that cosine theta is just going to be integrated, and we'll get sine theta. So we'll have sine of pi over 2 minus sine of negative 2, which gives us 1 minus negative 1, so it'll just be a 2. So this total force that we get from here is actually f of x equals 2 times p r h. So there we go. Now we just need to set this equation that we had for our pressures, forces, and that will just equal what we have here, which is our tensile strength times 2 times T times H, and you can already see that some of these terms are going to cancel out. So that's going to equal our pressure times our radius times our height. Something to note here is since we're taking it of a gas, each of these gases that, if we take it as a gas, we can, we don't have to split up our pressure force into anything. We already know that what our pressure is based on the fact that it's a gas, so we could just find it, find that value very easily. If it was a fluid, we would have to kind of break it up and find it a different way. So what we have canceling out, we have our 2's are gone and the height. So we can see that our height really does not affect our thickness of our cylinder. So what we're gonna get is our T, our thickness, is gonna be equal to our pressure times our radius over the tensile strength. So we can see that that thickness depends on our pressure, our radius, and our tensile strength to see this minimum pressure. And whatever we get from this equation, that's gonna be the minimum thickness that we have of our cylinder. So if we're thinking of in design terms, nobody would really use this actual thickness. It would probably be a lot larger, or a little bit larger than that, because they don't want to use the minimum thickness to take this pressure. For this problem, this is very similar to our cylinder problem, except we're going to be finding the thickness of a sphere that can take the pressure of some gas inside of it. So what we have here is a sphere, some thickness, goes around like that, and we want to find this minimum thickness of our sphere so that it can take these pressure forces trying to escape. So how we want to look at this is, first we have to find, just like our cylinder problem, we need to find our total forces of those pressures that we're going to set equal to. So we have 2 times pi times the thickness times the radius. So this is how we're going to get it, and there's the usual way that we would get it was by taking the 2 different circumferences. So what that would look like is pi times r plus t squared minus pi r squared. So when we FOIL this out, we get pi times r squared plus 2tr plus the t squared, and then minus that pi r squared that we found earlier. So we can see from this, we can see that our pi r squares, those are going to cancel out, and we'll be left with a 2 pi tr right here and a pi t squared. So how we find this 2 pi tr is we have the 2 pi tr here, and then we have this pi t squared. When the thickness of this sphere is so small, in this case it's going to be very small thickness, we can just say that this t squared pi is going to be negligible, since this 2 pi tr will really be the value that matters in the end. So we can just get that to be 2 pi tr. I'm just going to erase what we have here and put this 2 pi tr at the top for what we'll have. So now we're gonna wanna take some cuts of our cylinder, or of our sphere, and figure out from those cuts what our pressure forces are. So I'm gonna put a coordinate system with the Z, X, and Y. So then we have that. What it's going to look like is we have object like that with our theta, some angle theta going out to our radius of our sphere. And then up top, this will be the radius, and we'll have some angle going out to that there that I'm going to label as phi. So now that we have it right here, we want to look at what we're really trying to find is this pressure force. So we're going to find those forces in the y direction, since we just wanted to pick one direction. So what we're going to have, we have these radiuses where the pressure forces are coming out, and we have some arc length that they're going to be forming as our area. So right here, we have this arc length at the bottom where our theta is, that I'm going to put as our d theta. So that'll be the angle of that arc length, and then up top we'll have another one that I'm going to say is our d phi. So now we're going to want to put, here's our total forces in the y direction are going to be equal to those differential forces times, we're going to have some angles, some sine or cosines that will give us what these forces are, these pressure forces are in our y direction. So I'm just going to hold off those for right now, but first I'm going to find these magnitudes that we have. So what we have here, we can see, is this arc length is going to be r sine of phi times d theta, and then up top this will be r, this arc length will be r d phi. So now we can put those into our pressure equation. We'll have our pressure times those two r's will be r squared times our sine phi times d phi times d theta. So now what we want to find is our these two angles that will give us our y direction. So we want to find, we're trying to find this pressure force only in this y direction right here. So that will just be this theta right here we can find. It will just be that sine theta. And then up top, we'll have the same thing, but it'll be sine phi. So, and we're going to want to add those. It'll just be sine theta times sine phi times our differential forces. So that'll also go right here. Now we can see that we can split up our integral into two different integrals, which first we can take out that PR squared, since those are both constants. So now we'll have that PR squared times the integral of sine phi squared, since we have two sines, sine phi's, and then times that d phi, and then that will be multiplied by the integral of our sine theta times d theta. So now we want to find our limits of integration that we're going to be taking for each of these. So since we're in a sphere, it's just going to be from 0 to pi for our phi's, and also 0 to pi for our thetas. So I'm just going to erase some of this, make sure I have room for our integrals so I can derive these. So what we were left with was PR squared, our Fy equals PR squared times integral of sine phi squared d theta, or d phi, from 0 to pi, times the integral of sine theta d theta from 0 to pi. So I'm going to derive this first sine phi squared first. So I'm going to use, for our sine, we have a property that we can use for this, which is sine A plus B. So sine A plus B is going to be equal to cosine A cosine B minus sine A sine B. So for this, we can plug in our sine phi squared, and we can put that as, it's going to be sine phi plus sine phi, or sine phi plus phi, which is just going to be sine 2 phi, which will equal cosine phi times cosine phi minus sine phi times sine phi. So those will just be cosine squared and sine squared. So now we can see, we can take our sine squared out and find that that sine squared phi will be equal to 1 minus cosine of 2 phi, or cosine squared phi over 2. So now that we have our sine squared phi, we can plug this back into our integral, and it'll be easier to derive that. So we have here is our, from 0 to pi, we have 1/2 minus cosine squared phi over 2. So automatically I can see that this 1/2 is going to be phi over 2 from 0 to pi, and then we have this cosine squared over 2, so it'll be minus, minus 1/2 times cosine squared of phi. So we're going to want to use our integration by parts here. So I'm going to take our u value and set that equal to 2 phi, and then our du will equal 2 phi. So this cosine squared phi, or this is cosine 2 phi, sorry. Cosine 2 phi over 2. So now we have our phi over 2 from 0 to pi minus, this will be a 1/4, since I took out that other half right there. So it'll be 1/4 times the integral of cosine of u. And now we can integrate that. It will just be minus 1/4 times sine, then plug back in our u's, and I will get sine 2 phi from 0 to pi. So now we can see that this sine 2 phi will be sine of 2 pi and sine of 0. And we can see those both are 0. So this whole term is going to be 0. So we're just left with pi over 2 for that first integral that we just took. So I'm just going to erase all this and put in this term is going to be our pi over 2. Next, we have this next integral is just a sine theta, so that would be easy to derive. So integral of sine theta is going to be negative cosine of theta from 0 to pi. We can see that that's going to be 1 minus negative 1, so it'll just be 2. So I'm going to erase that. So we have 2 here, and our pi over 2 there, so it'll just be pi. So now we're left with, so our total force for these pressures will be PR squared times pi. So now that we have all of our pressure forces, we can set it equal to this original value that we have, is our 2 pi TR. So that's also going to be multiplied by our tensile strength, since this sphere is made of some material that we need the tensile strength for. So that will be 2 pi times the thickness times the radius times our tensile strength is going to be equal to PR squared times pi. That way we can see pi's cancel out. This radius is now just one radius, and then we have the thickness. You take this tensile strength and the 2 over the other side, we have PR over 2 times the tensile strength. So that's what we get for our final thickness, is that T equals PR over 2 times the tensile strength. If you look at this problem again, the sphere problem, you can see, drawing it out, so you have the sphere, and if you take an area that's right in the center of the sphere, you have these pressure forces coming off your walls, or you have these forces coming off your walls to equate for the pressure. And you know that in this hemisphere, the pressure forces coming from that air, or the whatever gas you have in your sphere, you can see that these forces have to be equal to the pressure forces coming off of this gas right here. So if you look at that and you just take an area that's easy to work with, like taking that one right in the center, you just have that sphere, or that circle that you have, and just take that area of the circle, which is just going to be the pi r squared, and multiply it by that pressure that you get from that point in the circle, because you know that this plane right here of your sphere has to be pushing off those same exact forces to equate for the pressure, since this gas is not accelerating at all. So if you look at the same thing with the cylinder problem, you can see essentially everything's going to be the same, except this time your area that you're taking, you're going to do the same thing and take it just down the center, but your area this time is obviously not going to be a circle, it's going to be a rectangle. Since you have this area of this plane that you're taking, that's where the pressure forces are coming off of. And instead of having that pi r squared as your area, you'll have this height times, so you'll have your pressure, that same pressure that's equal and opposite to these forces from the edge of your cylinder. It will just be that pressure times your area, which you'll have your radius, which will be 2 times your radius, since that's your diameter, which is technically the width of your rectangle that you're taking, and your height. So it will just be 2 PR times your height. So that's another way that you can look at this problem, an easier way to find out how that relationship works.